introduce about Faraday's law. Faraday's law of electrolysis explains how the mass of a substance deposited at an electron depends on the electric charge passed through the electrolyte. So for the first Faraday's law says mass is proportional to the charge, while for the second Faraday's law says it's also related to the substance equivalent weight. Since charge equal current times to time, we get the formula is M equal to KLT. In this experiment, copper 2 nitrate was used and the copper ion were reduced at the cathode. The goal was to see how mass changed with time and confirm Faraday's law. So the objective of the experiment was to investigate Faraday's law of electrolysis by measuring the mass of copper deposited on the cathode at different time intervals during electrolysis. First thing first, the copper strips are cleaned by using a sandpaper before it being used in this experiment. Then the copper strips are rinsed with distilled water and we will dry it by using a hair dryer. Second, the strips are weighed and the mass is recorded in the table provided as an initial mass. Third, the strips are dipped into a 50 cm strip of 1 mole copper 2 nitrate solutions. Fourth, the time is started as soon as the circuit is complete for the reaction to occur. Next, the reaction is led to react for 10 minutes. Then the copper strips are removed and cleaned by using distilled water and we dry it by using hair dryer. Then, once it dry, the final mass is recorded in the table provided as a final mass. We will repeat step from 2 to 7 for 50 minutes, 20 minutes and 25 minutes.
For these experiments, at 4 different time intervals, 10, 15, 20 and 25 minutes, we recorded the initial and final masses of both electrodes. Here are the results. These results clearly show that as the reaction time increases, the mass of the anode decreases and the mass of the cathode increases. This is consistent with Faraday's law, which states that the amount of substance deposited or dissolved at an electrode during electrolysis is directly proportional to the quantity of electricity passed through the electrolyte. For the calculation part of this experiment, we analyze the change in mass at both electrodes, the total charge passed, and compare the actual mass deposited to the theoretical mass predicted by Faraday's law. At each time interval, we calculated the change in mass at the cathode, delta M, which is increases from positive 0.76 gram at 10 minutes to positive 1.75 gram at 25 minutes. The total charge passed, calculated by multiplying current and time, ranging from 3,600 coulomb to 9,000 coulomb. The theoretical mass of copper expected to deposit using Faraday's law, which is theoretical mass, equal to mQ divided by NF, where M is the molar mass of copper, Q is the charge, N is the number of electrons transferred, which is 2 for the copper, and F is the Faraday's constant.
The experiment clearly supports both of Faraday's law of electrolysis. As the electrolysis time increased from 10 to 25 minutes, we observe a proportional increase in copper mass deposit on the cathode, confirming Faraday's first law that the mass deposited is directly related to the electric charge passed. Since the current remained constant, the charge increased with time and so did the mass. Faraday's second law was also confirmed as only copper was involved and its equivalent weight stayed constant throughout. However, our percentage yield slightly decreased from 63.87% to 59.12%. In conclusion, the experiment successfully validated both of Faraday's law while also highlighting common experimental limitations. These findings reflect not just theoretical accuracy, but also practical challenge in real-world electrochemical application such as electroplating, metal purification, and battery technology.